My name is Lu Li. I'm an interim chair of Department of Physics here. Really welcome you all to come to the fourth lecture of 2026. Before I start, let me say that we have YouTube viewing online. So we have wonderful audience there, and also like to see the welcome to the people on the stream, and welcome, of course, the another community who has been coming to different public lectures, Ford, Taoyo Wu, as well as Saturday Morning Physics. It's such a great community. We really appreciate that you will all be here with this wonderful lecture. So this lecture is made possible by generous donation from the Ford Motor Company. We are really grateful to them. Let me ask that if in the audience, if there's any former Ford employee. Oh, wow, welcome, welcome. Please, please, let's thank them. This is. Yeah. I have to say that we tried all the best way to reach to the Ford or for the board or whatever, and realize many of names, familiar names, are either retired or left or get better jobs. But thank you, thank you. And as we all know, Ford is the one of the key part of this state, right? It's great for present and future. And again, we're really grateful for the general support from Ford, for companies and many others employees there, to physics and the community. Okay, good. Just some announcements. The Q&A session, we always have a lot of engaging questions coming from the audience. And because this is a broadcast online, please either come to the mics so that you can line up and ask questions, or if you have questions, you raise your hand, then we have many wonderful students, volunteers who can bring the mics to you. So please wait for the mics so that we, the speaker, as well as the audience online, can listen to. The other thing is, of course, right after the Q&A session, I know many of you would like to come here and have a private chat with our wonderful speaker. Please wait until we finish taking photos together and then come to have a longer chat there. Okay, so good. So without further ado, I'm going to have another colleague, Professor Stephen Forrest, the Peter A. Rackham Distinguished University Professor of Engineering, to come here and give the introduction to our speaker. Please, Steve.
Thanks, Lou. My wife just reminded me that when I graduated from undergraduate school, I went to work to a branch of Philco Ford. So there. That was a long time ago, folks. Anyway, it's my great pleasure to introduce this year's Ford Distinguished Lecturer, Professor Richard Friend. So Professor Friend is a globally recognized leader in physics and material science whose pioneering research has revolutionized the field of organic electronics. This is a class of soft materials, or soft semiconductors, based largely on carbon. And they differ in so many interesting and exciting ways from conventional hard semiconductors such as silicon. Professor Friend is based in the Department of Physics at the University of Cambridge. His work has led to transformative technologies, including the first polymer organic light-emitting diode, high-efficiency organic solar cells. I think we might hear a little bit about some of this today, and organic transistors. His current projects include materials with unpaired electron spins that show novel couplings of spin with luminescence, and perhaps these too will lead to even newer and exciting applications that we have yet to imagine. He's a co-founder of multiple high-tech companies and a recipient of numerous international honors. He bridges fundamental science and real-world innovation and applications. His lecture will provide a rare opportunity for us to hear from one of the world's most influential physicists who's driving the future of energy and electronics. Professor Friend is a Fellow of the Royal Society and the Royal Academy of Engineering and is a foreign member of the U.S. National Academy of Engineering. Among other distinctions, he is the laureate of the Millennium Prize for Technology in 2010 and received the Harvey Prize of the Technion Israel Institute of Technology, and has won the Hippel Award of the Materials Research Society in 2015 and the Isaac Newton Prize of the Institute of Physics in 2024. He was knighted for services to physics in the Queen's Birthday Honors List of 2003. So please join me in giving a warm welcome to Professor Friend.
Wonderful. Well, it is a huge privilege for me to be here. I think I've turned this on. Oops. Okay. I'll start again. It is a wonderful occasion. I'm very privileged to have been invited here. I've had 2 wonderful days on campus. I am so impressed with what I find here. That fusion of new ideas, which you might label as science, and their translation into doing something useful, which is usually called engineering, really happens here. And I think that's when everything ticks, everything works, everyone's pleased with what they're doing. So it's been very uplifting to have been here, and that's what we should all be doing. I'm going to give you a talk about using molecules and how they can be used in semiconductor devices. I have to say, in the physics world, this isn't naturally where physicists tend to go looking, because materials that are not very crystalline and soft and have an affinity for water and might do chemical reactions, it doesn't feel like a happy space. But really, that's where a lot of the action is. So I was trying to work out where to start. And I'm going to ask you, which semiconductor device has been made in the largest quantity globally? And I'm going to start with silicon. And I was looking on the web and getting wildly different numbers, so I chose a large one. I'm not sure that it's right or not. But it might be 10 to the 14 CMOS transistors made per person on the planet last year. It's quite a large number. Another measure is that if we take all the silicon, 12-inch silicon wafers and use them to cover some space, it's about 10 square kilometers. It's quite a lot of very expensive wafers. But that actually is nothing, absolutely nothing, compared with the most dominant semiconductor device on the planet, which is the reaction center in photosynthesis. That's why life works. Here is an image of, it's actually from courtesy of the Fleming Group in Berkeley, these images. Photosynthesis harvests light from sunlight, eventually reduces carbon dioxide to make sugars. The first step is light gets absorbed in molecules that are colored. Unlike silicon, which is like a Model T Ford, which is black, the real world is colorful. Nature has made things of all sorts of colors. Whenever it makes something colorful, it's for a reason. And very often it is to harness sunlight. So there are molecules that absorb light. The electronic excitation in a magical way is funneled down to a bit that really is a diode. It's the reaction center. What happens in the reaction center is that the energy, the molecular excited state, I'll probably call it an exciton later, causes an electron to leave one molecule and move to the adjacent molecule. And that electron is then funneled away quickly, and it does reductive chemistry. eventually it produces sugar. The hole left behind, so here is a little element of the reaction center. The key to the indication that these might be semiconducting molecules is that they're planar. They're like little bits of graphene. But the hole, so an electron heads off this way, a hole ends up, if I look at it carefully, I probably won't do that, is a waste product. It actually oxidizes water to produce oxygen gas, which is pretty lucky because otherwise we'd have nothing to breathe. But if you look at what it is doing, it is the most exquisite photodiode produced in vast quantity, constructed with a very specific protein structure around it, designed so that the funneling of excitations produced by light absorbed further away from it is precise and brings everything to the right place. And then there are these channels to move the charges away and do chemistry. If you want living proof that you can do semiconductor physics with molecules, have a look at a green leaf. It's doing it all the time. So in stumbling ways, we've been, since the 1980s, trying to see if we can take synthetic alternatives where, rather than the exquisite organization that you have in photosynthesis, we can sort of sandwich them into diodes and use them to make solar cells, or use them to make light-emitting diodes, or we can place them on electrodes and make them work as transistors. A lot of what we do compared with what nature does is still very crude, but it turns out to be quite effective. And a lot of the lessons that are there in photosynthesis are things we've painstakingly learned, that yes, you can make things work. So what works? Here is the sort of quick chemistry lesson. This chain here was very important for us in Cambridge. We were working with that in the late 1980s. I don't know what it means to, I know what it means to me, but I realize others might see it differently. What we have are benzene rings, and then this is a vinylene linkage here, and it happens to be a polymer chain. The polymer chain doesn't matter very much. What do they look like? This one here would look like, here it is in solution. It's a sort of fluorescent yellowy green dye. So how do we think about the electronic structure? Well, for those who are aficionados of graphene, or graphite as we used to call it, graphene is when we take a carbon sheet with just carbon atoms. It would form a honeycomb network. We know that carbon has valence 4. In graphite or graphene, we have just 3 bonds onto each carbon. Those are the strong single bonds, keeps everything together. But left over is a pz electron, which overlaps with pz electrons at every other site to form delocalized wave functions like the states which allow electrons and holes to travel freely in silicon. We have the same ingredient. In the case of graphene, the band gap is 0, it's black, and it's metallic. In the case of our materials, and what I've shown here with this overlay in blue, is that this polymer chain, if I took a pair of scissors, I could construct it out of a sheet of graphene. I can go from graphene to a graphene ribbon. And in doing so, it's become colorful. We've opened up an energy gap between filled pi and empty pi star states, and we're in business to use it as a semiconductor. So that's one example, but that generically opens up a huge, limitless set of possible molecules we can design and use. So something we were doing, originally we were actually working with polymers to make transistors, which we managed to make work in the late 80s. But in various ways, we ended up making very, very crude structures. We had here's a glass substrate with a transparent layer of conducting indium oxide. We had spin-coated a layer of our polymer to make a thin layer, maybe 1/10 of a micron thick, and then evaporated a more a low work function metal. Here it's calcium to make a diode. And remarkably and slightly, I mean, if we'd read the literature, we might have realized it should have worked. It made quite a good light-emitting diode. You need to take with a pinch of salt. Here, I don't know whether you can see it at the back, but that is a little strip of light through a glass window in a brass vessel, because we had to keep the thing evacuated because it didn't like oxygen. But that was enough for us to see that we had actually made a light-emitting diode with this organic semiconductor and an incredibly crude structure. That crude structure has become more sophisticated, but the basic element, the reason that we are in business in this space, is that these heterogeneous contacts between different materials are or can be stable, and the fact that we can mix and match materials has given a huge flexibility to be able to build up electronic structures, electronic architectures to our designs. Now, of course, it's a huge step to what you all have. I mean, everyone in this room possesses at least 1 million organic light-emitting diodes, because every smartphone that you bought, as long as yours isn't 10 years old, the display is a pixelated display of red and green and blue organic light-emitting diodes, more sophisticated than that crude one I showed you in the previous slide, but operating in the same way. An incredible engineering achievement done very substantially in Korea and commercialized by, in the end, by Samsung and later LG. But these are organic molecules, not so different to the polymer I showed you, that are cheerfully glowing when electrically excited. They're now the dominant display technology. They have displaced liquid crystal displays because they're more power efficient, they give better color quality, they're faster, they're better. So I'm going to show you something to go back in time a bit, going back 20 years. I should mention, I've got some names here, Lele Chua, Peter Ho, both professors now in Singapore, Jana Zamzijl in Heidelberg, and my then junior colleague, but professorial colleague, Henning Seringhaus. Between them, we sorted out how to make a light-emitting transistor. So there's a bit more to the device here than I showed you previously. We start with a glass substrate. We pattern it to put some electrodes on. We're going to put 3 electrodes on. It's a transistor, so we have a source and a drain. It's colored yellow on the diagram because indeed it is shadow masked gold. For this structure, the distance across the channel is huge. It's 20 microns, so that we can see what's going on. We have put down a layer of organic semiconductor. For those who like the chemistry, it's this. It has a very similar coupled benzene ring structure to the one I showed earlier. That tells us that it's going to be a semiconductor. It again emits greenish light. Then we put an insulator on top, and this was a spin-coated layer from solution of polymethyl methacrylate. And then there's an evaporated top layer of gold, which is thin enough that we can get light through it. And what this does is both emit light and function as a transistor. So what is done with a transistor, with a field effect device, is to set up a high electric field across the insulator. And the electric field against a metal is trivial. I mean, that's sort of Faraday, Maxwell. We get a surface charge layer in the metal, but that's no big deal because we had lots of mobile charges to start with. But where the dielectric meets the semiconductor, that's more consequential because we inject electrons or holes, depending on whether the field encourages electron or hole accumulation in the semiconductor. And what's been done here is to adjust voltages. So we have a large voltage between the source and the drain, an intermediate voltage on the gate. So we can simultaneously induce electrons on one side, holes on the other, and there's an electric field that is pulling the charges in opposite directions. So as they drift, they meet, and we get a line of light. So I'm going to run the video, and just briefly you can make out black and gray stripes there. These are interdigitated electrodes, source and drain, And again, the channel length, the separation between them is 20 microns. So what we're going to see as it's actually what we're seeing as a change of gate voltage is light emerging from one electrode, and then as the gate voltage is controlled, we run the line of light emission across the device. You can see the fringe electric fields as you should do, and the video then ends up with the light disappearing as the line of recombination disappears at the other electrode. So it makes a great video. It hasn't made a useful device yet, but we can live with that. But what it does illustrate is we can move electrons around, we can move holes around, and when they meet, we can get light out. These are they are the elements we need to be able to do real semiconductor technology. Now, at this point, you might say, well, okay, that's it. It's all very obvious. So what's the big deal? Steve Forrest alluded to, in his remarks, to the fact that actually there are lots of big deals. If you pick up a textbook on silicon, you won't get the right answer. We live in a different materials world. There are some very fundamental differences, and I'm going to be slightly facetious in trying to explain what they are to appeal to the cosmologists in the audience. And I'm going to talk about multiverses. I was inspired by reading an excellent book on cosmology by Max Tegmark, who's on the faculty in MIT. And he was explaining how some of the consequences of quantum mechanics and inflation theory are that we have to contemplate that the universe we inhabit is not the only one out there. There might be parallel universes. And if you're feeling uncomfortable about that, the level of discomfort is then ratcheted up because we can have different levels of implausibility. We can start off with a level 1 multiverse where the parallel universes are just like ours. It's just that the Schrödinger cat was alive rather than dead or whatever in that parallel universe. And then we can step up to a level 2 multiverse where the laws of science, I can call them physics in this audience, because they're basically the same thing, are the same, but the fundamental physical constants are different because they're not that fundamental. And then you can go off to level 3 and level 4. And level 3, the laws of physics change, and I get lost at that point. But level 2 is actually something that us material scientists do without making a big shout about it. Let me illustrate. Let me look at what happens between two electronic charges, a proton and an electron. That's a hydrogen atom. But we know from Bohr theory that the lowest energy level compared to the vacuum level is a Rydberg below. It's the n equals 1 level. That's 13.6 electron volts. It's a huge energy. It's far too much to do chemistry. Chemical reactions have activation energies or bond strengths of the order of an electron volt or two. It's huge. And it's there primarily set by the Schrödinger equation and electrostatics. It's the potential, the Coulomb potential that does it. Let me jump to another parallel world where we've changed things. And this is an inorganic semiconductor such as silicon. And we've got the same Schrödinger equation. We usually call it the Mott-Vanier description of an exciton. I've now got the two charges are an electron and a hole, then that we've scrapped the proton. And they're sitting in a material, a silicon, which has a high background dielectric constant because there are all the other electrons around which are polarizable. So the electrostatic field is screened by the other electrons. So we've changed what we thought was a fundamental constant, which is epsilon 0, and made it 10 times larger by multiplying it by the dielectric constant. And then we turn on the physics that we have a crystalline lattice. So that's the polka dot structure there. And that causes us to rethink what mass is, and what turns out to look mass-like is the effective mass. It's fixed by the dispersion of wave-like propagation in a ordered structure. And for silicon and other inorganics, it's way below the electron mass, maybe 1/10 of an electron. So you up the dielectric constant by 10, drop the mass by 10, and what was 13.6 electron volts is now about 10 millielectron volts. I hope it's there. It's that little, I should have put that bolder. It's 1,000 times smaller. It's a completely different materials world. So if I photoexcite across the band gap in silicon, the electron and hole at room temperature will separate, so silicon solar cells work. So those are two extreme worlds, and very uncomfortably, if I can get this to work, the organics sit in the middle. They are not silicon-like. The interactions are quite strong, but they're still semiconductors. The key number for me is that the relative dielectric constant isn't 10, it's 3. And the masses, we can have a discussion about that, but they're of order of 1. So we bring the binding energy of electron and hole, which is the hydrogen atom, down, but maybe only to about half an electron volt. So if you take a molecule and absorb a photon, you won't get a free electron and a hole. You'll get a bound molecular excited state. You can call it an electron-hole pair if you want to, but it's held together by the Coulomb interaction. It's still the same Schrödinger equation, but we've got that intermediate set of masses and dielectric constant. Another consequence is that there's a very important energy that matters, which is the spin exchange energy between singlet and triplet, and that's the same Coulomb integral as the binding energy, and that matters. So we material scientists like our parallel universes too, and we've engineered them quite deliberately, and they work. So a little bit about excitons, molecular excited states. How should we think of them? These are some slides generated by one of my theorist colleagues in Cambridge, the group of Tommy Montserrat. It's fairly high-level calculations of what excited states look like. The molecule this time, I'm sorry to take you through a bit of a zoo of molecules, but if you're okay with graphene, you won't go far wrong. This is 5 benzene rings stuck together. It's called pentacene. The clue's in the penta. It is a dark red material. It absorbs light on the deep red and then across the visible. It crystallizes, and when we absorb a photon, the excited state is, we'd call it an exciton. Here's what the wave function looks like. So what has been done is to localize the hole on the central molecule and look to see where the electron sits. So it's not completely confined to that same pentacene molecule. There is quite a lot of overlap of the pi electron systems from one molecule to the next. And actually, there's significant occupancy of electron wave function on the nearest neighbors. So it's a much, much smaller exciton than you would get in gallium arsenide or silicon, but it's more than sitting on just a molecule. And that's in the singlet state. That's what we photoexcited. We start with doubly occupied valence level. We photoexcited one electron up to a conduction band level, so pi to pi star, and we're still in the singlet state. But of course, we can, in the excited state, swap the spins because we've only got single occupancy of those 2 levels and create a spin triplet. So here we have the 2 spins aligned. We have an S equals 1 state. And it has a huge consequence. What happens is that because the spatial wave function is now antisymmetrized, the 2 electrons in the excited state keep out of one another's way. So they may be sitting on the same molecule, but they're never in the same place. So the exciton shrinks from sitting over nearest neighbors to sitting on just one molecule. It's a very, very localized object, and its energy is completely different. It's about 0.9 electron volts. It's about half the energy gap. That's an extreme example, but this is an inescapable consequence of living in that intermediate semiconductor world where these interaction energies are large. So back to the light-emitting diode. We have our molecule in its ground state. If we photoexcited it, absorbed a photon, as you see for I showed you images of fluorescent materials, we would simply keep within the singlet manifold, just excite up, and then drop down again. We have high luminescence yields so long as everything stays in the singlet manifold. But in the LED, we bring an electron from one electrode and a hole from the other, and they meet in the middle, and they don't know what one another's spins are. So statistically, 3 out of 4 are triplets. And if the triplet was significantly lower in energy than the singlet, and it can't decay radiatively, we'd only get about a quarter of a photon per injected electron holes. And if that were all that would happen, we wouldn't have OLED displays on our smartphones. We do much better than that. So the key for red and green is work due to my local host, Steve Forrest, working with Mark Thompson now at USC. And I have to say, the other author on the Mark Baldo, then I think a grad student, has done quite well since, and is now at MIT. The trick is to use phosphorescence. If you can make an organometallic molecule where we have strong carbon to, this is iridium bonds. Iridium is way down the periodic table. The spin-orbit coupling is large, so that the differentiation between singlet and triplet is not exact. The triplet has got some singlet character. It can emit, it can phosphoresce reasonably quickly. It's about a microsecond rather than a nanosecond for the singlet. And for red and green, that's what happens in your smartphone. You've got some precious metal in there, not enough to make it valuable when you come to recycle it. But it turns out that the blue, although there are some very promising phosphorescent blues, at the moment they're not commercial. And the blue pixel does something quite exotic, which I will explain. It's a process of triplet fusion. So the proposition is that we bring electron and hole together. We form our molecular excited states. The 1/4 that are in the singlet configuration emit promptly. The other 3/4, we build up a long-lived population of triplets, because if we just have a simple hydrocarbon system, they live for a long time. And if the population can be large enough, and there's obviously some materials engineering to get things to work correctly, the decay mechanism is when 2 triplets bump into one another in an overall singlet configuration, and they fuse because and have enough energy to fuse to create one singlet. So it does take 2 triplets to make one singlet, and that can can double the efficiency from the blue pixel. So these are, it happens to be some work that was done in my group, but this is a small part of what has, for the most part, been carefully hidden away in the patent literature and industry. So what we've done here is to take one of our light-emitting diodes, drive it electrically, and then switch it off at this vertical line here. For some reason, it means it's 0.9 of a microsecond. It's actually the black line I want you to track. So we get a very fast drop in the amount of light that comes out, down to 55% of where it was. And then it runs very slowly over 10 microseconds. This afterglow, if you like, because we've got a population of triplets. The rate at which they decay is governed by the bimolecular kinetics of how they bump into one another. So as the population density drops, the rate of recombination drops, so that's the right kinetic. That very exotic triplet fusion is been extremely well engineered in current structures. Okay, when I started talking about photosynthesis, and I diverted into the light-emitting diode, which is something that nature hasn't found a reason to do, and it's turned into a massively important technology, and it's really been the existence proof that if something is well engineered, even if it wasn't stable to start with, and they weren't, they can do a fantastic job. And what's exciting is that there's far more that will be done with OLEDs. They will become significantly better. Let me turn back to photosynthesis, or what we would regard as organic solar cells, where the story is one of work in progress. The dream, I mean, this isn't a particularly useful image, but it's just to put you in mind of it, is that it would be nice to make solar cells that use less material. Photosynthesis, green plants are very efficient users of material. Even the best silicon solar panels have to be out in full sun for many months before they've repaid the energy burden that was required to make them. Green plants simply wouldn't grow if they had to wait 6 months to get a payback on the investment in growing. We think the payback is measured in days, not months. And the reason is that they use material very efficiently. So I'm making an inappropriate and unjustified connection between using less material and being as good as green plants. But there have been some interesting developments to architectures which are still extremely crude compared to photosynthesis. There's an enormously important work from Ching Tang, then at the Kodak labs in Rochester, and I should say that he did something similar that got the OLED field going, where what he did was to make, and this is from his original paper, and graphics weren't so good back in the 80s. What has been done is to vacuum sublime 2 semiconductor layers, one of them an electron donor, and one of them an electron acceptor. And the idea is that if the energy levels are offset, if we've got sort of valence and conduction levels for one material and the other has the levels offset, we can photoexcite in one, and then it's energetically favorable for the electron, say, to move from the donor to the acceptor, and we've achieved charge separation. The problem is that you have to have light absorbed right at the interface between the donor and the acceptor. The donor and the acceptor are the equivalent of the special pair in photosynthesis. In photosynthesis, the excitons are funneled very deliberately through to the reaction center. Here, the reaction center is sort of distributed over that interface, and it's not very efficient. So the innovation, which happened in many ways across the materials world, but in the organics, involved taking donors and acceptors that were co-soluble in the right solvent and getting the conditions right so that when the solvent is taken away, you end up with an interpenetrating network of donor and acceptor where the length scale for the feature sizes in this network is small enough that it doesn't matter where a photon's absorbed, the excited state will diffuse and find an interface, and that will then give the charge separation that's needed. It's amazing it works, but it does. The image on the left here is of a very early structure using a polythiophene as the donor and C60 fullerene as the acceptor. The scheme, in this case, it doesn't make an efficient solar cell, is that the donor, we photoexcite an electron up to quite a high energy, and then fullerene is a very good acceptor, and the electron transfers across, actually losing quite a lot of energy, so the open circuit voltage is rubbish. But that's the charge separation step. There's been a lot of work. We've abandoned fullerene. There are a whole set of materials which are generically called not fullerene, which doesn't describe what they really are. And a lot of wonderful work, principally in China. And there are now quite a few organic solar cells which have a power conversion efficiency in sunlight above 20%. Silicon can do 25%, lead halide perovskites can do 25%. So 20% is good, but probably not good enough. I'm not going to say much more about it, but one of the things that we know is problematic is the same problem that we have in LEDs, that which is that when electrons and holes combine, we'll form triplets more frequently than we do singlets. And in a working solar cell, Shockley quasar, detailed balance thermodynamics, we know that photons come in, they generate electrons and holes. We can extract some of them through the extraction electrodes, but electrons and holes recombine. And so long as they re-emit a photon out, that's still efficient. What goes wrong is when an electron and hole go dark, they produce an excited state that doesn't emit, and that's the triplet. And some of our work, we've been, whenever we go looking for these triplets in solar cells, we find them. I think Steve and I agree on this. The rest of the community is in denial. But we have to find new ways to engineer out the triplets. I'm not going to say more about that this afternoon. Okay, well that's, if you like, a sort of general background. What I'm now going to do is to talk about things we've been doing in Cambridge in the last few years, where we've made things different by starting off with a molecule that has an unpaired electron. These are called radicals. Maybe I'll save it up for questions as to why they're stable. Just trust me that they're okay. So here it's a radical that's been around in the literature, I think, for most of a century. We have, again, benzene rings onto one carbon, which has only got 3 bonds. So there must be a PZ carbon orbital that's got 1 electron on it, and that's a radical. It actually delocalizes, its wave function does delocalize onto the 3 rings. It's actually quite an interesting object because that there's quite a lot of symmetry protection for the electronic state, that non-bonding orbital, to do with the electron-hole symmetry that is present in that sort of simple structure. There's lots of work on radicals. Electrochemists love them. You can make very good batteries with radicals because you can do redox chemistry. You can reduce, you can oxidize reversibly. But in general, they're not very bright. So there's some very interesting work that came from a group in Barcelona, in Spain, 20 years ago. What they did was to attach chemically a donor group, a bit like the solar cell, but with a different function here. It's a carbazole group, so we have a nitrogen and 2 benzene rings. And the photoexcitation that you get when you absorb a photon transfers an electron off the nitrogen, it's a non-bonding orbital, and puts it on the carbon non-bonding orbital. So we end up with a positive charge and a spin here, and a negative charge and no spin there. That's the photoexcitation. And it goes both ways. So they're actually quite bright. That's an example, and that was very consequential. So we ended up, we had a very good group in China, in Jilin University. The Feng Li is the has led, and he spent some time with us in Cambridge, and he taught us a bit about these materials. I should mention Emrys Evans, who did a lot of the physics on our side. But what we discovered is that these materials are extremely luminescent. We had luminescence yields with the quoted figure we had back then was 86%. It's really good because the emission is surprisingly red. It's out beyond 700 nanometers. That's sort of beyond red. And that's fantastic, a high luminescence yield. Anything that's bright is interesting. But what's really interesting is that the singlet-triplet problem morphs into something that isn't a problem. So let me just explain what I had said in words with the diagram here, that we start with 2 electrons in the highest occupied molecular orbital, or valence state. It's actually associated with a nitrogen here. We have a single electron on this singly occupied molecular orbital. The optical transition is to take an electron up and then down. That's absorption, that's emission. That's what I've described. So where is the triplet? Well, it won't be a triplet, it'll be a quartet. Yes, I've managed to go in the wrong direction. Okay, it'll be a quartet. If I wanted to get a high spin state, the cheapest I can do it is to singly occupy the pi, the non-bonding level, and the pi star. Now, the way I've drawn it, you'll agree with me that's a higher energy state. It really is after it's been done methodically. Just changing the occupancy of the levels to start with has just changed the problem. We no longer have a problem. We've now got a molecule that is bright and its lowest energy excited state is emissive. So the triplet problem has gone away. Just as a brief aside, and I will pass by this slide quite quickly, it's really interesting to be able to get very high luminescence yields down in the deep red and the infrared for molecular systems, because usually there's a problem that vibrational modes coupled to the pi star excitations, they modulate them, and molecular systems have high frequency vibrations, so you don't need many of them to span the band gap when you get down to the infrared. So luminescence yields fall off a cliff as you get down into the infrared. If you go looking for dyes to do confocal microscopy, fluorescence microscopy, you'll discover that the infrared ones are rubbish. But we discovered some rules, and essentially the one that works best is where the excitation is from non-bonding nitrogen to non-bonding carbon, because the non-bonding levels are vibrationally decoupled. They have the symmetry protection, so that's why we can keep the luminescence yield up. So this small change in coupling between these two, essentially, they're just sort of isomerically different. We've dropped the quantum yield from 90% to 14%, and what we've done is to inadvertently get a sort of pi conjugation on the left, so the most accessible valence state is now pi, and it has all this vibrational coupling. So this very small change in coupling can completely change the luminescence. So those are some rules. Very briefly, we can make quite good LEDs. I've chosen some examples where we're emitting at 800 nanometers, which is useful. It's where the window in biological materials sit. I show you this slide just to illustrate that modern OLEDs have many, many different molecular materials put down sequentially by vacuum sublimation for the most part, and that makes it possible to funnel in electrons and holes and get them to recombine to produce light in the right place. So here we have our radical there. And in this paper we published 2 years ago, we had just under 10% for emission at 800 nanometers. There's some unpublished work, sorry, I'm going the wrong direction, from my postdoc, Seong-jae, where he's redesigned the stack. We've added some protecting groups onto the radical, due to my chemistry colleagues in Cambridge, and we've now got a forward efficiency of 13.3%, which, given that not a large fraction of light goes in the forward direction from an OLED, points to to a luminescence yield of about 40%, which at 800 nanometers is very high. So that was the way we started with the radicals. The big surprises have happened in the last couple of years when we look at what happens when we couple spins. Because what we've ended up with by good fortune is molecules that have, they're luminescent, each of them has a spin, and we can chemically couple them, do covalent coupling to control how much conjugation, how much tunneling there is from one unit to the next, and explore what they do. So at this point, forget about organics, and those who work in the inorganic world, this might seem familiar. This is straight out of Neville Mott's book on metal insulator transitions. There are many, many antiferromagnetic insulators that, if you didn't worry about Coulomb interactions, would be metals. Many of the oxides of the first row in the transition elements, like nickel oxide, are antiferromagnetic insulators. The reason is that the bandwidth that would delocalize electrons isn't large. The intercoupling, atomic coupling T isn't large. And it's quite expensive. If you want to make something metallic, you have to move an electron from one site to the adjacent site, and that's sort of zeroth order modeling costs a repulsion energy. Putting two electrons onto the same orbital costs what's usually called the Hubbard U. It's quite a large energy. As I'll show you in our case, it's about 1.8 electron volts. So that description where we have localized spins, I've shown as a chain, but of course it can be a three-dimensional structure, where the excitation, which by the way fixes the exchange energy, the excitation costs an energy U. It can only happen if we have antiferromagnetic coupling between the two adjacent sites. So we have opposite spins, and we can excite an electron, move an electron from one site, leaving behind a positive charge, put it on the adjacent site, a negative charge. It's cost an energy U. In perturbation theory, that gives you the exchange energy. That is the description of a large number of inorganic materials. That is what cuprate superconductors look like if they're undoped. When you dope, they can be metallic, but undoped, they're insulators. And actually, that's what we can do with our molecular system. That same excitation is what we can engineer in. I'm going to take you an example of a diradical. And what's what we discovered was known a very long time ago, back in 1950, but is not something that is seen in the inorganics, is that transition, that charge transfer state, is coupled to photons. Although the symmetry of the states is the same, there's a movement, there's a dipole, because we're moving charge, so it is radiatively coupled, and we can see it. So here is, now I apologize for the chemistry. As there are more carbon atoms, the molecule is displayed smaller and smaller. Let me very quickly show you the bits that matter. We have the same unit of the benzene rings with a spin on the central carbon, which is coupled just three of them here. There's another one here. And then we've put in some rings, benzene rings, to put in conjugated coupling. I should mention Petri Murto working with Hugo Bronstein and Cambridge Chemistry, who came up with this. The coupling I can go into in some, for anyone who's interested, I can say more about it. But it's chosen here that these two spins have a very weak antiferromagnetic coupling. You have to go down to 1 Kelvin to get the two spins to be in a singlet state. At room temperature, it's 3/4 triplets and 1/4 singlets. They're bright. So this is a blue laser coming in. Colors are always rather strange when they're photographed with iPhones, but there's plenty of red light streaming out from, this is a film of this in polystyrene. The spectrum is, you can see here, there's a peak at around 640 nanometers, another peak at about 700 nanometers. You might think that one was a vibrational overtone of the other, and there's some of that in there, but it turns out to be rather unexpected, and it was my student, Ritipano Chowdhury, who spotted this. The most convincing demonstration of this I can show you is experiments he did in the group of Alexei Chapelyansky in Paris. If you want to get free access to a dilution fridge with optical access, that's the place to go to. And he's a brilliant colleague. So here we have the same material in a dilution fridge at 1/4 Kelvin, so it's cold. And if we start with the red curve, which is no magnetic field, we're down at 1/4 Kelvin, so the spins are anti-parallel. We've got the singlet state, and the emission is peaked at 700 nanometers. Now I turn on the magnetic field, and actually only needed a Tesla, but here it is at 7 Tesla. The color has changed. The peak is now at 640 nanometers. So I've turned on a a Zeeman energy, which is in Kelvin, I've changed the color by thousands of Kelvin. The color has simply switched. What has happened is that although the ground state energies are very little different between singlet and triplet, when we go to the excited state, everything changes. And the reason is that if we start with the triplet, the only excitation I can go to is one that involves conduction band levels, pi star states, and they're quite high energy. But if I started with a singlet, there's a lower energy excitation. It's that same excitation of the Mott-Hubbard chain. I'm moving the electron from one side, from one radical to the other. I have a positive charge, I have a negative charge, but I've lost spin. And that, and I can, if I animate, I'm going to try and animate that. What you can see is, as we've done the charge transfer, I'll run it again. It's cost a charging energy, but that charging energy is less than going to an exotonic state involving the pi star state. So it's that charge transfer state that is the singlet, which is redshifted, and the regular exotonic state that is the triplet. Now, another way of measuring that, and I should say this, the emission from the singlet is slow, it's beyond 100 nanoseconds. That energy shift, the 700 nanometers, is exactly what you measure if you do electrochemistry. If you look at the difference between the reduction and the oxidation potentials, which is telling us the difference between 0 or 2 electrons on the site, it's the same answer. It's the right answer. So what we've got is a sort of molecular analog of what is much investigated as a sort of spin optical qubit, and that is the nitrogen vacancy defect in diamond. And that is a very, very useful object because it is possible to optically polarize the spin state. The ground state is a triplet. Triplets are good because they have the multiplicity of the sublevels in the triplet. But there's a singlet manifold as well, and you can optically cycle, and as you intersystem cross between triplet and singlet and triplet, that's how you can build up these non-thermal populations of the sublevels in the triplet. And that can then be very easily detected by bringing it into microwave resonance, and that then changes the luminescence. So you can measure spin state from optically detected magnetic resonance. So these are slightly different radicals. These are meta-linked phenyl or pyridyl links here. So some work that Michael Wasilewski has been doing in Northwestern. And the most remarkable property that we discovered is that the luminescence is affected by tiny magnetic fields. In some of them, there's a fluence dependence. I've obviously taken the best example to put on to show you. We can get a 10% reduction in the luminescence in 2 millitesla. 2 millitesla is sort of 50 times the Earth's magnetic field. It's a small field. It's fringe magnet territory. It's not a big field. It's a tiny energy. How on earth is it modifying the luminescence? It is a surprise. It's less of a surprise if we do magnetic resonance. These are measurements of optically detected changes in luminescence as there is magnetic resonance brought to bear, but within the manifold of the triplet levels, the T plus, T minus are higher in energy than the T0, and if you bring the right microwaves in to bear, then you can mix the change the occupancies of the levels as the resonance is driven in. So these are measurements done in the group of Sam Bayliss with Alistair Ingalls in Glasgow, and what we can see, what we're doing here is that at 0 field, we can pick up, there are actually 2 resonances at about 50 megahertz and 100 megahertz, depending on whether we're looking at the ground state or the excited state resonance. And then if you put a magnetic field on and further split the levels, the we get these wings as we'd expect as the level splittings vary with field. So we know what is changing. It is due to the magnetic field affecting the spacings or that are there in the triplet sublevels. I put a little bit more in here. This is, if you look at the luminescence plots, the black is with and the red is without, the black is without, the red is with magnetic field. There's a small, you can see the reduction up at the 640 peak. The differential change, the delta PL upon PL, shows a suppression of the triplet and actually moving towards an enhancement of the singlet out at longer wavelengths. That's telling us that at least part of what's happening is that when the magnetic field goes on, it's increasing the intersystem crossing from triplets to singlets. It's possible to time resolve that. These are measurements that Alexei had done. So we're looking at the luminescence in black decaying. It's a logarithmic scale here, a time scale from 0 to 100, 120 nanoseconds. The red curve is the differential luminescence, the difference between 0 and 5 millitesla. And you can see there's a big change that runs out to about 30 nanoseconds. That's the time scale. We can actually see where we are altering the intersystem crossing. So there are some analogies. The analogy that we think is most relevant is some very beautiful work done by several groups. The one I'm most familiar with is Peter Hoare in Oxford, where over many years they've established that a number of songbirds move around to navigate using the S magnetic field. This is the European robin. And they do that because they have molecules in the back of the eye, things called cryptochromes, which when they absorb light, separate charges to produce two spins, a cation-anion radical pair, initially in the singlet state, but they will intersystem cross, and how the intersystem crossing runs depends on what the magnetic field was, and remarkably, the evolution to triplets can be chemically detected, and that's how they sense field. It's a very small field they sense. It's actually comparable to our sensitivity, and the reason we can measure small fields is because the spins are quite far apart. They're about a nanometer apart. Usually triplets, as you saw earlier, are very, very close. The two spins are very close together. So in the NV center in diamond, that triplet splitting is about 2 gigahertz. We're at 50 megahertz. That's the difference. So 50 megahertz, I only need 2 millitesla to get the same Zeeman energy. That's why it works at these really low fields, and that sort of makes it useful. So here comes a movie. So what we have here is our sample. It's excited with blue light, which you can see in the image, and there's some red light coming out from the sample. And on the left is Kyung's laptop showing the luminescence signal. And when I run it, what you'll see is Ritu bringing a fridge magnet. It is a fridge magnet close to the sample, and then you can see the luminescence very visibly dropping. I showed you the graph, and you all glazed over and took no interest. As soon as I show you the video, it comes to life, doesn't it? It is strange. This is quantum mechanics in action. It's so surprising. The sort of rider, which is not yet on archive, is that Ritu and Samarpita Sen, who works in one of the biosciences labs at the Gurdon Institute in Cambridge, she is expert with confocal fluorescence microscopy. And what you do with confocal electron microscopy to image biological material at confocal resolution is introduce fluorescent dyes. and then Z-scan and get 3D imaging. So this image here is of the egg of the fruit fly. The scale bar here is 50 microns. The mauve is a standard dye. It's a fluorescein phalloidine dye that heads to the cytoskeleton, so you can see it's gone fairly specifically, and its brightness is what you see. Our dye radical is the red. It hasn't gone to the nuclei. Remarkably, you can put it into DMSO, then add some buffer solution, and it doesn't fall to pieces, and you can introduce this into biological material. It's not very specific, but it goes for hydrophilic parts of the structure, and you can see it there. And then I can put, or they have put, the 5 millitesla field on, and you can see it's quite visible. We do a different spectrum. It is possible to modulate the luminescence in this biological context. Maybe we shouldn't be so surprised, because I did start talking about photosynthesis, where we have these molecules that you might think of as being just about to be oxidized and be useless, but they're happily photosynthesizing for us. And here we're using them to do some sensing. So that's where I want to finish. And I should mention some funders, the Engineering and Physical Sciences Research Council in the UK, the European Research Council, which I have to say is the absolute savior for many of us. Fortunately, the UK rejoined the European Research Council scheme in spite of this foolish decision to leave the European Union. And then we've had some wonderful funding from the Simons Foundation. But thank you for listening.
Thank you for the wonderful talk. Thank you for the wonderful talk. Yes, please, either you come to the mics to ask questions, or raise your hand for questions.
Question, I can see that.
Please wait for mic. Yeah, for the audience. Yep. Oh, here we go.
In the February Journal of Nature, there was an article about three-dimensional projections from computer screens for education. What kind of light source are they using in that kind of project?
I have no idea. I'm sorry. I could make it up, but that probably wouldn't be helpful. I think I better go and read it.
Last month, and I was very excited
Right.
about seeing without any devices that are projecting 3D screens for use in medical school and science, physics education.
I mean, usually 3D requires separate projections I mean, usually involves wearing polarizing glasses and picking out different polarizations. I mean, okay, I don't know. Yes, yeah. Sorry, I can't be. Yes, I'm not going to guess.
Thank you for the amazing talk. I'm an undergraduate student, so I don't have a very advanced knowledge on physics yet, but I'm really interested in the bird migration. So I'm just kind of curious, could you explain the relation between the photoluminescence you measured in the organic material and how the bird migration like the...
That's a really good question. So our surprise discovery was that we get this magnetic field change the luminescence at very low magnetic fields. 2 millitesla is a tiny field. And the reason is that because the molecules have been built so the two spins are relatively far apart, about a nanometer apart, the splitting within the triplet manifold is quite small. It depends, it's a dipole-dipole interaction. It goes to the cube of the distance between them. So we're down at 50 megahertz. And if you work out what field gives a Zeeman energy that is equivalent to 50 megahertz, it's about 2 millitesla. So we're fairly happy about that. But it's a completely different regime to most molecular triplet spectroscopy, where most of the time the two electrons in the triplet are very close to one another. So that's That's why we've got this low field sensitivity. Then for the bird migration, the proposition is that quite as a protein complex at the back of the eye. It's not involved in vision, but of course, it's quite a good place to put something because there are lots of nerve connections, and it's quite a safe place to put a molecule. So these things are termed cryptochromes, which means hidden color, which is not very helpful. And the proposition is that light is absorbed. It's a bit like the organic solar cell I was talking about. There is charge separation, an electron and a hole separate. They don't really know exactly how far apart they end up, but the electron and the hole both have got spin, and probably they end up about a nanometer apart, as we've got. And the proposition is, although they might initially be generated as singlets, whether they choose to intersystem cross to become triplets depends on the external magnetic field, which is just what we were seeing. And with the Earth's field, that is sufficient to modify how many remain as singlets and which become triplets. And in ways that I certainly don't understand, that ratio of singlet to triplet ends up being detectable, and the bird brain can know what the field was. I'm making it sound, I'm leaving, I don't, I mean, it's massively complex, but the key is that you need two spins far enough apart that the Earth's magnetic field is able to reset the eigenstate for the total spin wave function, and that then determines how it evolves between singlet and triplet. You're nodding, I think you're nodding.
Yeah, thank you
Yes.
for the
Right.
clarification.
Yes.
So one is actually, is there any photoluminescence involved in the bird?
There is a recent paper from the Oxford group, which has come out in Nature. I've read the preprint, where they have managed to sort of use that and detect some luminescence similar to what we're doing. The difference there is that it takes seconds to build up the population of spins, because they start with no spins. We start with, we've built the spins in. Nature doesn't know how to put spins in, but we have them to start with, so we get a fast response.
Thank you very much.
Clear that OLEDs are the preferred technology for displays now. Partly the gentleman, yourself and Steve, have brought that about. But for lighting, I believe still gallium nitride-based diodes with phosphors are the dominant. Is there any potential for OLEDs to become useful in lighting? And what are the barriers and why?
The thing that we don't do with organics is to drive them very bright, because they don't like getting hot. I mean, the dirty secrets will come out if you press hard enough. So they can be pretty bright at screen level, but if you look at how bright gallium nitride LEDs are in lighting, it's much, much brighter. And for lighting, it's interesting to see how it played. Originally, so-called white lights were not at all white. They were pretty unpleasant because the blue is down-converted with phosphors to give something that has the semblance of white, but it didn't used to be. So you never got any red in the early nitride LEDs. They're now quite good, and they're very cheap.
Thank you so much for the great talk. It was really interesting to see such a great effect with such a small magnetic field. And I'm wondering, and you mentioned that is because of the separation. It's quite large. I wonder whether that can be tuned with different distance, and especially when it gets to larger and larger. Is there a limit for that?
Okay, this is a really good question, and the short answer is we haven't explored increasing the separation. We do have a system where we've reduced the separation, and we've seen the magnetic resonance shift up from 50 megahertz to 250 megahertz. So, you know, the 1 over r cubed law is correct, but we haven't systematically gone to greater distances. The chemistry isn't trivial, but it's a really good question, yeah. It might be that we've hit the sweet spot straight away, but we of course, will investigate. Yeah.
I would argue that temperature dependence is quite interesting too, right? Such a small energy, and yeah, room temperature is working. Thermal broadening is not killing that. If you contrast your 7 Tesla, you need 250 millikelvin.
But magnetic resonance is pretty weird. I mean,
Sure.
you can do NMR at room temperature, where the energy difference between nuclear spin up and nuclear spin down is extraordinarily small.
That's right.
They're not thermalized when we're doing this. You have to scratch your head and.
Yeah, I know. Yes. Any further questions? Well, thank you.